You're going to have to bear with me while I figure all this out. Okay, so I want you to look at this graph. Tell me what this is. It's a line. You agree with that? Yeah. Okay, and I couldn't get the grids to do what I wanted to, so looks like a line, right? We're all good with that. Okay, so what happens?
Oh my gosh, I'm too good for this.
Yeah, I didn't zoom in far enough if you could see that it was curving. I meant to zoom in farther. But it totally looked like a line, right? Would you agree with that? So let's look at this point right here. If we're at 4, 2, this point right here. Okay, if I were to draw the tangent line to that, it would look like this. Okay, that's a line tangent to the curve at 4, 2. Okay, you with me on that? If we zoom in really, really far, farther than I was so it doesn't look like a curve, they look like the exact same thing, right? So not just at 4, but really, really close to 4, whatever that tangent line is a pretty good approximation for the value of the function as well. Would you agree with that? And the farther I zoom out, the more we can start to see the curve here and how it changes. But like all of this right here, that's a pretty good approximation. Even if I found a point on this blue line, that's pretty close to what the value is of the green curve. Would you agree with that? Okay, so what we're going to look at today is linear approximation. Okay, when we can't figure out from a curve, we're going to look at it linearly. So here are your notes for today, linear approximations. Okay. So this says, and I'm sure nothing else up here is going to work right either. I should have, yeah, that's what I thought. There we go. Okay. Shh. Pay attention. What are you doing? Okay. Linear approximations. Are you paying attention? The tangent line to a curve, so tangent line to a curve, we've been talking about tangent lines a lot, gives us a useful way to approximate a value on the curve. It's an approximation, okay? We usually write our tangent line equations in point-slope form. So although we have been using the official point-slope form, y minus y1 equals m times x minus x1, I kind of left it like that for a while because I wanted to make sure we were really comfortable with that, right? Ooh, y minus y1. But it's going to be helpful if we start actually doing this, which means one of two things. You can write it like this, like you've been doing, so you don't mess anything up, and then move this y value. That totally works. Or you can remember that if we have, let's say that we had, let me just make these up, a slope that's equal to 1/2 and a point that is at, I don't know, 3, 4. It doesn't even matter. Okay, and we wanted to write an equation for that line, right? We know how to do that, and we can do the y minus y1, whatever. But if we want to jump to this form right here, we do y equals the slope, which is 1/2, times x minus the x value, close my parentheses, plus the y value. And remember what you learned from transformation, that x is a big fat liar, right? So same thing kind of goes in here. This is like in the transformation form. This is positive, but it looks like x minus 3 because x is a liar. This is positive, so it's positive out here. Okay, so whatever you got to do, we got to get it into that form. If it means we write it like this and then we move the y, or if we just know how to write it like that, that's fine too, either way. Okay. So we're going to look at the following graph. So this is kind of the same type of thing that we just looked at, where we have the function f of x, so that's red. I know yours isn't red. And then we have the tangent line. Okay, is yours red? Did I print? Oh, I did print it in color. Look at me. Okay, so from this graph we can see that x equals a, so there's my a value, right? The tangent line and the function have nearly the same graph. Really close in here when we zoom in. It's nearly the same. Obviously it's very different as we go out, but on occasion we'll use the tangent line, because we can do tangent lines, which is L of x, as an approximation for the function. Approximation near x equals a. So the approximation f of x is about f prime of a times this is called the linear approximation or tangent line approximation of the function at x equals a. It's important to know if the linear approximation is over or under approximation. There's going to be a couple of ways that we know that. We're going to talk about one of them now, and then we'll talk about another one after we get into the next section and learn a few other things. So we have concave up and concave down. That may not be something that we've really talked about much before, but hopefully it makes sense. You've talked about concavity in science, right? So concave up can hold water, concave down it doesn't, okay? Yeah, in like 7th grade is when you first talk about it, when you talk about lenses, right? Concave, convex. So concave, so you talk about concavity, right? So if it's concave up, it's like it's a bowl, it can hold water. Concave down, the water's going to empty out, okay? So the concavity has to do with the curvature, up or down. We good on that? You look at me like I'm crazy. Is this a hard thing to understand? Okay, well, there we go. Okay, so if f of x is concave up, do we understand how this looks like concave up? Yes? All right, so if we have a tangent line, so I'm going to draw tangent lines here. Thank you for the... All right, so if I have a point here, I have a point here and here. Oh, my board is going to be weird. This is the actual point, and this is the approximate point. Okay, approximate and actual. And over here, I'm going to extend my line just a little bit. And this one is also my actual point, and this is the approximation. Stop it. So do you see how the approximate value is going to be less than the actual value when we're talking about y values, right? It's underneath because it's concave up. So what this means for us is that if it is concave up, tangent line lies below the graph. Lies below the graph. Okay. Therefore, the approximation is less than the actual. So that means it is an underestimate. You know what that means? Okay, good. Okay. If it is concave down, so notice if it's concave down, do you see how no matter where I draw my tangent line, it is above the curve? Over here, no matter where I draw that tangent line, it's below the curve, right? So that's kind of the important thing that we're looking at here. So if I draw these, like so, it's hard to get this on here right, okay. So this is these will be the actual right here. And this is the approximate. Okay, so the approximate and the actual. So if this is concave down, my pen is way too thick, and I'm not going to mess with it right now because I can only do so much. Okay, so the tangent line lies above lies above the graph. Therefore, the approximation is greater than the actual. Okay. So right now, the only way we can tell if it's an over approximation or under approximation is if we know something about the concavity. We're not going to always know something about the concavity. That's why there's another way to do it. We're just not there yet. In my opinion, it would make more sense to do this when we got there, but nobody asks me my opinion because I don't know if they still trust that I know what I'm doing. All right, so concave up, concave down, right? Approximate is an underestimate. The approximation here is an overestimate. That's something that we'll have to explain in our answer if it's an overestimate or an underestimate. Okay, so you need to think, and if you need to say, all right, well, if it's concave up, then if I draw my line, I can see that the line's underneath it. That's what makes it an underestimate. If I draw this, and say, okay, I draw that, I know it's above it, that's what makes it an overestimate. Okay, so you can draw yourself a little sketch, or you can just visualize it, whatever works for you. So it's important to look at the concavity on the interval, so we have to explain it in intervals, from the point of tangency to the x value. So example justification, the approximation of f of 1.1 using the tangent line at x equals 1 is an over approximation because it's concave down on the interval from 1 to 1.1. Like we have to actually speak about an interval, which we'll get there when we get there. Okay, so let's try this example here. Ooh. All right. So we let f of x equals this. We need to write an equation for a tangent line. If we're going to write an equation for a line, we need two things. What do we need? A slope and a point. Okay. So we need a point, and we need a slope. Okay. We want this at the point where x is 1. So we need 1, and then f of 1, right? I need to actually figure out what the y value is. So I can go up here, I can find f of 1. F of 1 is going to equal to the natural log of 3 times 1 squared is 3, minus 2 is 1, plus 2. What's the natural log of 1? 0. 0 plus 2 is 2. So my ordered pair is 1, 2. So then I need the slope. The slope is going to be f prime of 1. So I need to find f prime. Would we agree with that? Okay, so f prime of x equals. So we take the derivative of a natural log. Whatever the argument is for the log is in the denominator. 3x squared minus 2. And then the numerator is the derivative of whatever's in here. So the derivative of 3x squared minus 2 is just 6x. And then when I take the derivative of 2, it's 0. Okay with that? We've been writing that as 1 over that times 6x, but it ends up being that. We should be able to jump there. So then I need to find f of 1. So f of 1, I'm sorry, f prime of 1. It's going to be 6 over 3 minus 2. So that is 6. So I have my slope, and I have my point. Everybody with me? So I write the equation of the line. My equation is y equals my slope, which is 6, times x minus 1. And then what comes next? Plus 2. Okay? That is the equation for the line tangent to the graph at the point where x equals 1. Everybody okay with that? So now I want to use the equation. So I use the equation I just did and approximate f of 1.1. So f of 1.1, this is super important here, is approximately, right? I have to have squiggly equal signs because it's not equal to. It's approximately, and I substitute in 1.1 into here. 6 times 1.1 minus 1 plus 2. That equals 6 times, what's 1.1 minus 1? 0.1 plus 2. What's 6 times 0.1? 0.6 plus 2 is 2.6. Notice my notation here. F of 1.1 is approximately, then we have this, and then this equals, because these two things are equal, but they are approximately f of 1.1. Okay, we okay with that? All right, so because I don't know what this graph looks like, I don't know if it's concave up or concave down. That's the only way I can tell if it's an overestimate or underestimate right now. So then we're just going to have to save this for later. We can't really answer C right now. No, we actually still won't use a calculator. There's just a whole nother process. Okay. All right. Let's look at the next one. Now this one gives us a graph. It's like the SAT, yeah. Okay, suppose that the only information we have about the function is that f of 4 equals -2, and the graph of f prime of x is shown below. Use linear approximation to estimate f of 3.9. Is the estimate too high or too low? And explain. Okay, so if we're going to use, if it tells me linear approximation, that means I'm going to have to write an equation for the tangent line so I can actually estimate it like we just did, right? In order to write an equation for a tangent line, I need a point and I need a slope. Okay? What is the point that I can use? What? 4 is my x value. What's my y value? -2. There's my ordered pair. We understand where we got that? We got it from this information right here. So my slope then, I need f prime of 4. What is f prime of 4? Can I find a derivative? It's 6, because it tells me the graph of f prime of x. This graph is f prime of x. F prime of x. F prime of x. Okay, that graph is f prime of x. So f prime of 4, I go to 1, 2, 3, 4, and that's at 6. Okay, we okay with that? So then I'm going to write the equation in my line. Y equals the slope, which is 6, times x minus 4 minus 2. I want to estimate this. I'm using that equation to estimate f of 3.9. So I can say f of 3.9 is about 6 times 3.9 minus 4 minus 2. All right, 3.9 minus 4 is -0.1. So this is 6 times -0.1 minus 2. So that's -0.6 minus 2, it's -2.6. And this is, the graph is of f prime, not of f. So we don't know if f is concave up or concave down at this point because we are looking at the prime. So once again, we're not going to be able to talk about the estimate being too high or too low right now. Okay, we good with that? Okay, what questions you got? All right, let's at least start this one here. So we're going to consider the differential equation. That's just a fancy way of saying the derivative. So I have the derivative is equal to 3 minus y times the cosine of x. We let y equal f of x be the particular solution to the differential equation with the initial condition of f of 0 equals 1. The function f is defined for all real numbers. So we want to write an equation for the line tangent to f of x at the point 0, 1. And we're going to use the equation to approximate this. Okay, so we're going to write the equation for a tangent line. For that, I need a point And I need a slope. Do I have my point? Yes, it is 0, 1. I need the slope, which means I have to evaluate the derivative at 0 or at 0, 1 at this point, right? So I need dy dx evaluated at 0, 1. So I need dy dx evaluated at the point 0, 1. So I substitute it in here. So that's going to be 3 minus what? 1 times the cosine of what? 0. So it's, what's the cosine of 0? 1, so that's just 2 times 1 is just 2. So my slope is 2. Any questions about where anything came from? Okay, so then I write the equation of my line. Y equals the slope, which is 2, times x minus 0. I'm going to just write x minus 0 because I already opened my parentheses. Could I have just put x? Yes, I could have. And then plus 1. So when I want to approximate f of 0.2, that's going to mean that f of 0.2 is about 2 times 0.2 plus 1. What's 2 times 0.2? 0.4, so that's 1.4. What questions we got? We good? Any questions? All right, perfect. All right, so we are going to stop there. I'm going to give you the assignment so that you can have it and you can start working on it.